To the section 4.4 lecture video on concavity and curve sketching. One of the things we're going to skip over a little bit in this lecture, just to tell you off the bat, is some of the graphing portion of this that's in the note sheet, just because you guys all have graphing calculators, the ClassCalc app, so you shouldn't really need to know how to use this information to draw the graphs by hand. But you should understand how the derivatives relate to what the graph looks like. So that's what we're going to spend more of our time on here today. So we had the first derivative test last time. So now we're going to talk about concavity and the second derivative test. So the graph of a differentiable function y equals f of x is concave up on an open interval I if f prime is increasing on I, and concave down if f prime is decreasing on I. So if we look at the graph here, concave down simply means that the graph is the rate at which the graph is going up is getting smaller and smaller. So concave up means that is increasing. So that's how those relate. And this gives you a good picture of what concave up and concave down look like. So a function whose graph is concave up is also called convex. The second derivative test will allow us to check for concavity, because just like the first derivative tells us the rate of change for the first derivative, for the function, the second derivative tells us the rate of change for the first derivative. So if f double prime is greater than equal to 0 on I, then the graph of f over I is concave up. If f double prime is less than 0 on I, the graph of f over I is concave down. A point C, f of c, where the graph of a function has a tangent line whose concavity changes, is a inflection point. At an inflection point, C, f of c, either f double prime of c equals 0 or f double prime of c fails to exist. Find the intervals where the graph of the function is concave up and concave down and the coordinates of any inflection points. So to do that, we need to find the second derivative of the function. So let's do that. Start by finding the first derivative. So the first derivative here would be negative 9 minus 12x minus 3x squared. And the second derivative would be negative 12 minus 6x. So we can set that equal to 0. So negative 12 minus 6x equals 0. So negative 6x equals 12. So x equals negative 2. So the inflection point is going to happen at x equals negative 2. And then what we want to know is, well, what happens on either side of that? Okay, so basically, based on that, I have two intervals. I have the interval from negative infinity to negative 2, and I have the interval from negative 2 to infinity. Those could either both be concave up or concave down, but most likely one of these is concave up and one of these is concave down. So to find out which one is which, we plug in a number in each one of those intervals. So a number in that first interval is negative 3 into the second derivative. So that'll be negative 12 minus 6 times negative 3. So that equals positive 6. So that means this interval is concave up. And then if I plug in a number in this other interval, like 0, I get negative 12. So that's concave down. And then to find the inflection point, I simply find f of negative 2. So plug that value, negative 2, into the original function. So 1 minus 9 times negative 2 minus 6 times negative 2 squared minus negative 2 cubed. And so when we do that, so I'm just putting in my calculator. So the -2, we should get 3. So the inflection point is -2, comma 3. Okay. And the nice thing is you can see a lot of this from the graph. The only one it won't tell you is the where the inflection point is. So if you were to graph this, you could kind of figure out where it's going to be, but you wouldn't be able to actually tell for sure. Okay, so this also allows us to use the second derivative to test for local extrema. So suppose that f double prime is continuous on an open interval that contains x equals c. If f prime of c equals 0 and f double prime is less than 0, then f has a local maximum at x equals c. And if f prime of c equals 0 and f double prime of c is greater than 0, then f has a local maximum in c. And if f double prime of c equals 0 and f double prime of c equals 0, then the test fails. The function f may have a local maximum, a local minimum, or neither. Okay, so let's go ahead and give this a try to put these tests together. So what you want to do is you want to first find the derivatives. So y prime here would be 1 minus cosine of x, and y double prime would be sine of x. Okay, so now what we want to do is we want to set both of those equal to 0 to find inflection points and critical points. Okay, so let's go ahead. So if we set 1 minus cosine equal to 0, x equal to 0, then that's cosine of x equals 1. So the cosine of x equals 1 in this interval at 0 and at pi. Oh, no, never mind. At pi it equals -1. At 0 and at 2 pi. So these are our critical points. Okay. And then we can set the other one equal to 0. Sine of x equals 0 to find inflection points. So sine of x equals 0 at 0, pi, and 2 pi. So these are our inflection points. Okay, and so we can try and use this information together to figure out where is this graph concave up, concave down, and the local maximum and the local minimums. Okay, so one of the interesting things that happens here is we can't use the second derivative test to find local maximum and local minimum, because notice that when f prime is 0, sine f double prime is also 0. So the points we would be concerned with here, trying to work with this, so the x values we're looking at are 0, pi, and 2 pi from the information we have right here. And so we could find f of those, f prime of those, and f double prime of those. So f of 0 would be 0. F of pi would be pi. And f of 2 pi would be 2 pi. F prime at these points, well, f prime is at 0 and 2 pi is 0. And at pi, it would be 2. And f double prime is 0 at all of these. Okay, so things we know here. So we know we have critical points at 0 and 2 pi. We know we can't use the second derivative test to figure out their local maximum or minimum, but we can use the f values. Okay, so since we know these are critical points and this has the smallest f value, I know that a local min is 0, 0, and a local max is 2 pi, comma 2 pi. Okay, and then I know there is an inflection point at pi. And at 0 and at 2 pi, but it turns out that those are also maximums and minimums, local maximum and minimums because of this. But the inflection point here is going to be at 0, comma 0, pi, comma pi, and 2 pi, comma 2 pi. Although we won't include, since these are endpoints, we won't include them as inflection points because the graph doesn't go concave up or concave down beyond them. And so then the last thing we need to figure out is we know we're going to be concave up and concave down in the intervals from 0. Oh, wait, that's not the one I wanted. Sorry, I wanted to keep the middle one, pi, comma pi. And then we know we're going to be concave up on the intervals around this point. So we're going to be concave from 0 to pi, we're going to be something, and from pi to 2 pi. And to check which one is which, we need to plug a number. We need to use this second derivative test for concavity. So we need to find out what is the second derivative on that interval. So we need to plug in a number into the second derivative that falls in those regions. So if I plug in, for example, for this one, if I plug in a number between 0 and pi, so pi over 2 of sine is 1. So that means this would be concave up. And if I plug in 3 pi over 2, sine of 3 pi over 2 is negative 1, so that means this one is concave down. And that's the idea. So when the second derivative is 0 at a point, we can't really use it, which is why I needed the f values. And if I graph this, I think all of this will be bared in mind. So let me go and graph this so you can see it. So let's graph in radians. So that's good. That's set up. Y equals x minus sine of x from, and then I want to add in a domain. So from 0 to 2 pi. Okay, and if we zoom out a little, we can see this. So we've got a minimum value over here on the left-hand side, a maximum value over here on the right-hand side, and then there's a concavity point in the middle where the concavity changes. We're concave up first, then we have an inflection point, and then we're concave down. So that worked out exactly how the calculus said it should. So let's go ahead and try another one. So we do the same thing we did with that one. So first find the derivative. So y is that? Y prime is negative 2 minus 2x, and y double prime is negative 2. Okay? So a couple things we can do here. So we can find the critical points. So the critical points are when this is 0. So critical points. Okay, so negative 2 minus 2x equals 0. So negative 2x equals 2. So x equals negative 1. And then inflection points are when the second derivative equals 0. So negative 2 equals 0. Well, that doesn't work, so there are none. Okay, so there are no inflection points. And so we get our critical point, which is at negative 1. And if I want to get the second coordinate for that, the y coordinate, I just plug that into the original function. So in the original function, that gives us 6 plus 2 is 8, minus 1 is 7. So this should be negative 1 comma 7. And now all I have to ask is, well, what's the second derivative at this point? So at x equals negative 1, y double prime equals negative 2. So that's negative. So that means that it's concave down, which means this is a maximum point because y double prime is less than 0. And then the last thing we can do is concavity. And because the second derivative is constant, that means it will have the same concavity everywhere. So from negative infinity to infinity, its concavity is it has a derivative of negative 2, second derivative of negative 2. So that means it's always negative, which means it's concave down. So this graph is always concave down. And this is a parabola that opens down, which should make sense that it would be concave down. It's always facing down. Okay. So there's a couple examples. So now what we're going to do is move on to the next thing, graphing these, but I'm not going to worry too much about the graphing. I just want to do the same stuff we just did. And some of this, like I said, you're going to be able to figure out just simply by graphing it using your Class Calc app. So let's take a look at that first. So if I graph, sorry, let me make sure I got that right. Yep. If I graph y equals x to the fourth plus 3x, plus 2x cubed, yeah. 2x cubed. Okay, so what you can see here is if we look at this graph, we can see where we expect the critical values to be. We expect them to be at negative 1.5 comma a decimal, and we expect it to be at 0 comma 0. And where we expect the critical values to be, because that's where we expect the slope to be 0. And only one of those is a minimum. Okay, but if you look, what happens at the other one is actually that the concavity changes, right? This graph you can see is concave up till there's an inflection point somewhere between negative 1.5 and 0, where it changes to concave down, but then it goes to concave up again. Okay, so let's go ahead and take a look at doing the calculus for this. So using the graph together with the calculus is a really good idea. So I would graph all of these before you start working on them, just so you know what they look like to start with. So the first derivative here is 4x cubed plus 6x squared. And the second derivative would be 12x squared plus 12x. Okay, so now we're going to set both of those equal to 0 and solve to figure out where our critical values are and our inflection points. So critical and inflection. Okay, so the critical is 4x cubed plus 6x squared equal to 0. Factor out a 2x squared, and you're left with 4x plus 3 equals 0. Oh, oops, sorry. Nope, I didn't factor out the 2 on the first term there. 2x plus 3. Okay, set those both equal to 0. and you're going to get x squared equals 0, so x equals 0, and subtract the 3, so 2x equals negative 3, divide by 2 to get x equals negative 3 halves. Okay, and then we can do inflection points. So we've got 12x squared plus 12x equals 0. Factor out of 12x, and that leaves you with x plus 1 equals 0. So 12x equals 0, x plus 1 equals 0. So we get x equals 0 or x equals negative 1. Okay. So from this information, we can see a few things are happening. So one, we have an inflection point at this critical value. So that means that this is not going to be a maximum or a minimum, right? Because the maximum or minimum needs to be positive or negative to a maximum or minimum needs to be positive or negative to have a maximum or minimum there. So we know that we're only going to have a maximum or a minimum at this value of the other ordered pair, negative 3 halves. So let's go ahead and work out which one of these are which. So we've got, these are inflection points. So let's first figure out what these are. So this inflection point is 0, 0. If I plug 0 into the original function, if I plug negative 1 into the original function, I get 1 minus 2. So that's negative 1 comma negative 1. So we've got those figured out. We can also plug negative 3 halves into the original function to get this, well, we could get these ordered pairs. So that's 0, 0. And this one, so negative 3 halves to the 4th plus 2 times 3 negative 3 divided by 2 to the 3rd. So that is negative 27/16. So negative 3 halves come in negative 27/16. So there's our ordered pairs. Okay, so now what we want to do is we want to try and figure out the concavity of everything that's going on here. So to figure out, first of all, to figure out the concavity, what we want to do is we've got 3 regions here, right? So we've got we can do, our regions would be negative infinity to 0. To negative 1. Negative 1 to 0. And 0 to infinity. And then we just need to decide what is the value of the second derivative in each one of those. So plug a number from each one of these into the second derivative. So we can do y double prime of negative 2, y double prime of negative 1/2, and y double prime of 1. So y double prime of negative 2 is going to be negative 2 squared is 4. 4 times 12 is 48. Plus negative 24 is positive 24. So this will be concave up. Negative 1/2 squared is negative 1/4. It's positive 1/4. So that's 3 plus negative 6. So that's negative 3. So that's down. And then the last one, if I plug in 1, I get 12 plus 12, which is 24. So this is concave up. So that's all the concavity regions. We've got our inflection points. And then we know 0, 0 is not going to be a maximum or a minimum because it's also an inflection point. But then we can check what is the value of the concavity at negative 3 halves. So negative 3 halves falls into this first region, negative infinity and negative 1. It's concave up, which means this is a minimum. And all of that we found using the calculus is exactly what we expected, exactly what we found. and try this one. So same idea as the one we just did together. Start by finding the derivatives. So the first derivative here is 4x cubed minus 4x. And the second derivative is 12x squared minus 4. And then we can set those both equal to 0. So for critical values and inflection points, so 4x cubed minus 4x equals 0. Factor out an x. You get x equals 0 or x squared equals 4. So x equals plus or minus 2. And then we can do the same thing for inflection points. So we've got 12x squared minus 4 equals 0. So that'd be 12x squared equals 4. So that would be x squared equals 1/3. So that would be x equals plus or minus the square root of 1/3, which is x equals plus or minus root 3 over 3. Okay. So now that means, so now we can find all the critical points and inflection points. So the critical points would be, we've got -2, so we plug -2 in, and you get 16 minus 8, so you get 8. Plug in 0, and you get 0. Plug in 2, and you get 8. Okay, and then we've got our inflection points. So we've got -root 3 over 3. So if you plug that in, you'll get 9 over 81. So 1/9 minus 3 over 9. So I believe you'll get -5/9, but let me check that with a calculator. Yeah, so you get -5/9. And if you plug in positive root 303, since you're taking it into even powers, you'll get the same thing. Okay, so there are inflection points. So now what we just need to do is our concavity, and then that should also tell us our maximums and minimums. So concavity, we've got the regions from -infinity to -root 3 over 3. We've got -root 3 over 3 to root 3 over 3. And we've got root 3 over 3 to infinity. So now we just plug in values from each one of those for the second derivative. So we could do the second derivative of -2, the second derivative of 0, and the second derivative of 2 for those. So the second derivative of -2 would be -2 squared is 4. 4 times 12 is 48. 48 minus 4 is 44. So 44. So that's concave up. At 0, we get -4. So that's concave down. And at 2, we get 44. So that's concave up. So that makes -2, 8 has a positive second derivative. So that would be a minimum. 0 has a negative second derivative, so that's a maximum because it's concave down. And then the last one is also a minimum. Okay, and that's all there is to doing that idea. So let's go ahead and try this one more time with the next one, and then we're going to look at doing this with non-polynomial type functions. So this one we do the derivative. Y prime is 2x minus 2 over x squared. The second derivative would be 2 minus plus 4 over x cubed. So find the critical and the inflection points by setting those equal to 0. So 2x minus 2 over x squared equals 0, and 2 plus 4 over x cubed equals 0. So multiply both sides by x squared to get rid of the fraction, so you get 2x cubed minus 2 equals 0. Add 2 to both sides to do 2x cubed equals 2. Divide by 2 to get x cubed equals 1, so x equals 1. Over here, multiply both sides by x cubed to get 2x cubed plus 4 equals 0. Subtract 4 from both sides to get 2x cubed equals negative 4. Divide both sides by 2 to get x cubed equals negative 2. And then take the cube root of both sides to get the cube root of negative 2. Okay, so we think this graph has got a critical value at 1 and an inflection point at this cube root of negative 2. So let's see what that looks like. So we've got, if we plug 1 back into the original, we get 1 plus 2, which is 3. And if we plug the cube root of negative 2 back into the original, the cube root of negative 2 cubed, oh, that's going to be an interesting number. But it would be the cube root of 4 plus or minus plus 2 over the cube root of negative 2. Okay, and so and then I think we could actually simplify that a little bit, because if we yeah, so let's go ahead and try and simplify this. So we can multiply by the cube root of 4 over itself to make this into, or negative 4. So this would be the same thing as the cube root of negative 2, cube root of 4 minus, I can bring the negative out in front. If I multiply by the cube root of 4 over itself, this becomes an 8, and the cube root of 8 is 2, so this is 2 times the cube root of 4 over 2. These cancel, they subtract, so it should be the cube root of negative 2 comma 0, which is a nice little simplification, which we could actually graph that. If you wanted to graph the original function and see if that makes any sense at all, you could. X squared plus 2 divided by x. Yeah, and it looks like we do have an inflection point right at a negative decimal and 0. So that appears to be, yeah, so that should be correct. The other thing we're missing here is that there is a place where this is undefined, which I skipped over, but the function itself is undefined at 0. So that means at 0 we have an asymptote, which you can see in the graph. So the other thing we want to keep in mind is that x equals 0 is undefined. Okay? So when it comes to concavity, that 0 plays an important part in that. So we end up with the regions from negative infinity to the negative cube root of 2, from the negative cube root of 2 to 0, because that's where the the asymptote is, and from 0 to infinity. So if you plug numbers from the original, from these regions into there, negative 1 is in this region. Negative 2 is in this region. So I could plug negative 2 in. Negative 2 is 4 plus negative 1. So that would be 3. So this would be concave up. Negative 1 is in this region. So negative 1 So that's 1 plus -2, so that's -1, so that would be concave down. And then the last one we could plug in 1. And 1 plus 2 is 3, so that's concave up. So then 1 is in this last region, so it's concave up, so that means this is a minimum. Okay, so that's the idea. So now that we've looked at some things that involve things that look like polynomials, let's dive farther into this idea of undefined. So let's look at some functions that are rational. So the first thing you can do that's slightly different with these is you might want to include where is this function undefined in your initial steps in this problem. So this function is going to be undefined at x squared minus 2 equals 0, which means it's x squared equals 2, which means it's undefined at x equals plus or minus the square root of 2. So that's going to be important as we move forward with this problem. Okay. So then the next step after that is we need to do the same things we've always done, which is we need to find the first and second derivative of this problem. Now, one of the options you could do too to go along with this is go ahead and graph it to start out, just like we mentioned before, to see if the graph can make our lives any easier. So if I graph y equals, y equals I don't know it. No, let's just do it this way. X squared minus 4 over x squared minus 2. The graph's going to help us out. So we already know where these asymptotes are. They're at root 2 and negative root 2. And we also see that we're going to have a minimum value at 0, 2. So if you wanted to, and you can also kind of see from the graph that there are no inflection points. So the nice thing for this is if you wanted to, you could just go from the graph the information you need here. So what I know here is that because of these asymptotes, I'm going to have intervals for concavity from negative infinity to infinity broken up by these intervals. So broken up by those. So I'm going to get negative infinity to negative square root of 2, negative square root of 2 to square root of 2, and square root of 2 to infinity. And we also know that we have a minimum at 0, 2. Okay, so those are all values we already know. And now we can do the same thing we would always do for concavity to figure out, we can look at the graph to figure out the concavity rather than having to plug into the second derivative. So if you look at this piece on the left, it's definitely concave down. Right, it bulges up, so it's concave down. The middle part is bulges down, so that's concave down, and then the part on the right bulges up, so that's concave up. So this would be up, down, and up. So when possible, use the graph and a little bit of algebra to figure this information out rather than using the first and second derivative, especially when you're dealing with things where you have to use the quotient rule. Okay, so that's a general idea of how that would work. And the same thing is probably true for the rest of these. So like if I graph the next one, so negative x squared minus 2x plus 1 over x minus 1. Well, there's actually an interesting thing that happens with this one. Oh, sorry, I got the wrong equation. No wonder it looks interesting. Okay, so this should be a minus x, not minus 2x. Okay. So this graph is, we can see a lot of the same things from this graph without having to do any work again, right? I can see the maximum and minimum. I can see that the asymptote is at that x can't be 1. And I can see that it's concave down on the left and concave up on the left and concave down on the right, simply by looking at the graph. So where possible, use the graph to help you answer these questions rather than necessarily having to do them by hand. Okay. Okay. But if we wanted to do one of these written out, we could. So let's just go ahead and try this one. So we do the same steps we did before, right? So first of all, I know this thing is undefined at x squared minus 1 can't equal 0, so x squared can't equal 1, so x cannot equal plus or minus 1. Okay, so that's one really important thing right off the bat. Okay, so now we can go about finding the derivative. So y prime would be the bottom times the derivative of the top minus the derivative, minus the top times the derivative of the bottom. Over the bottom squared. Okay, so that's x squared minus 1 times 2x minus x squared times 2x over x squared minus 1 squared. So that's y prime equals 2x cubed minus 2x minus 2x cubed over x squared minus 1 squared. So that's y prime equals negative 2x over x squared minus 1 squared. So there's y prime, and then we can do the same idea to get y double prime, so which I'll come up here to the top. So y double prime equals the bottom times the derivative of the top, which I'm going to call negative 2x, minus the top times the derivative of the bottom, all over the bottom squared. So y double prime is negative 2 times x squared minus 1 squared plus 2x times so I have to use the chain rule here. So 2x times 2x squared minus 1 times 2x all over x squared minus 1 to the 4th. So y double prime equals negative 2x squared minus 1 squared plus 8x squared times x squared minus 1 all over x squared minus 1 to the 4th. And then y double prime, I can do some factoring here. So I can factor out a 2x squared minus 1. So it's 2x squared minus 1 times the opposite of x squared minus 1 plus x squared over x squared minus 1 to the 4th. And then that's y. I can cancel out an x squared minus 1, and I can simplify in here. These x's are going to cancel. So this becomes a positive 1 times 2. So it's 2 over x squared minus 1 to the 3rd. Okay. So then we can, from those, the critical points, negative 2x equals 0. So x equals 0. There's a critical point. And at over here, inflection points, 2 has to equal 0, which can't happen, so there are no inflection points. And if we plug 0 back into the original, we get a critical point at 0, 0. And my concavity regions are going to be based on the asymptote. So I can do concavity from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. If you plug in a number in this first region like negative 2, it would be 4 over 3, so that's positive, so that's up. If I plug in 0, I get 0, so that's not necessarily helpful, so let's plug in So let's plug in a, oh, whoops, sorry, I plugged that into the wrong thing. All of these are going to have the same concavity because I'm plugging it into the second derivative. So the second derivative is, if I plug them into the second derivative, let's see what we get. So if I plug in -2, I get 4 minus 1 is 3. 3 cubed is 27, so I get 2 over 27, so that's positive, so it is up. If I plug in 0, I get -2 over -1, so that's negative, so I get down. And if I plug in 2, I get positive, so that's up. And because 0, 0 is in this middle region where the concavity is down, this is a maximum. Okay. So we can use this idea for any of these. It's just a little more complicated with these more complicated derivatives. And so in a case like this one, it's probably going to be easier to use your calculator. However, if it's not, you can always fall back to using finding the derivatives, just like we've always done. Okay, so the last thing in this section is the idea of figuring out what the graph must look like from the first and second derivative instead of from scratch. So we can figure that stuff out fairly easily using the ideas we've been talking about today. So if I know the first derivative, what I want to probably go and do first is just find the second derivative. So in this case, I'm going to use the product rule and the chain rule. So it's the first thing, so x squared minus 2x times the derivative of the second thing plus the derivative of the first thing times the second thing. So y double prime is going to be x squared minus 2x, and then I have to use the chain rule. So times 2 times x minus 5. The derivative of x minus 5 is just 1 times 1 plus 2x minus 2 times x minus 5 squared. And then we can use some factoring here. So if I factor out an x minus 5, then I can do some multiplication. So I can distribute this 2, so it's 2x squared minus 4x on this side. And over here, I can multiply the x minus 5 that's left times this. So that's 2x squared minus 10x minus 2x plus 10. And then combine like terms. So y double prime is x minus 5 times combine like terms, so we get 4x squared minus 16x plus 10. Okay, so there's our second derivative. So now we can use what we know about first and second derivatives to figure out some stuff about this graph. So for example, I know I can find my critical values by setting x squared minus 2x times x minus 5 squared equal to 0. And so I know I'm going to have critical values at x squared. So let's just do some factoring. So I can set this all equal to 0 and factor. So I can factor out an x equals 0. I've got an x minus 2 equals 0. And I've got an x minus 5 equals 0. So I've got critical values at x equals 0, 2, and 5. And then I can find the inflection points by setting this other piece equal to 0. So I've got x minus 5 equals 0 and 4x squared minus 16x plus 10 equals 0. And then if we solve those, we'll get x equals 5. And over here, I think we'll have to use the quadratic formula if I did everything correctly. So let's make sure I didn't screw something up back up here. Well, I think I'm pretty good with that. So x equals 16 plus or minus the square root of 16 squared minus 4 times 4 times 10 over 2 times 4. So that's x equals 16 plus or minus the square root of 96 over 8. So that's going to be 16 plus or minus 4 root 6 over 8, or x equals 4 plus or minus root 6 over 2. Okay, so there's all our inflection points and stuff like that. So now the things we know, I'll write concavity up here where I've got some runes. So concavity, based on my inflection points, I know where my concavities happen. So I've got 4, so I'm going to have negative infinity to 4 minus root 6 over 2. So 4 minus, I've got 4 minus root 6 over 2. To 4 plus root 6 over 2, and then 4 plus root 6 over 2 to 5, and then 5 to infinity. Okay, and so we can just plug in numbers that fit into each one of those regions into the second derivative and figure out if it's concave up or concave down. So the first one you could plug in 0, and so you get negative 5 times 10, which is negative 50, so that's down. The second one, you could plug in something like 2 would be in that region, so I could plug in 2, so that's negative 3 times negative 6, so that's positive, so that would be up. Then the next one, we could plug in something like 4. So that's negative, so that's concave down. And the last one, we could plug in something like 6. Which is positive, so that's concave up. And then we can figure out which region each one of these is in, and that'll tell us whether they're mins or maximums. So 0 falls into this first region, so that's concave down, so that makes this a max. 2 falls into the second region, so that's concave up, so that's a min. And then 5 does not have at 5 the it's not in up or down, so that means that this is not a min or a max. Okay, so this is not an extreme. Okay, and based on all of that information, you should be able to pick out kind of what the graph looks like. So this starts out okay, so this graph starts out going up and concave down, and then we get to the maximum of 0, and then it switches inflection, and we get a minimum at 2, and then it has an inflection point at 5, and then it goes up forever like that. So the graph would look something like this. And so that's the idea behind how these problems would work. So you do the exact same steps you did before, you find the minimum and maximum values, and then you should be able to sketch a graph of what it would look like based on that. Okay, so let's go ahead and do this next one that I think will be a little simpler, hopefully, and then we can have you guys do one, and then we'll be done with this section. So y prime is sine of x, so the derivative of that is cosine of t. So to find the critical values, we let sine t equal 0, and to find the inflection points, we let cosine t equal 0. So sine t equals 0 at 0, in this interval 0, pi, and 2 pi. And cosine t is 0 at pi over 2 and 3 pi over 2. Okay, so we've got our, then we can do our concavity. So we go from 0 to pi over 2, and from pi over 2 to 3 pi over 2, and from 3 pi over 2 to 2 pi. The end. So the 0 and the 2 pi come from the fact that the interval we're doing is only from 0 to 2 pi. And so what we know is that, so then we plug a number for this into the second derivative. So into cosine of t, so like we could plug in pi over 4. So pi over 4, the cosine of pi over 4 is positive, so this is concave up. Here we could plug in the cosine of 0. We could plug in pi. Cosine of pi is negative 1, so that's down. And here we could plug in something like 7 pi over 4. And the cosine of 7 pi over 4 is the same thing as negative pi over 4, which is positive root 2 over 2. So this would be up as well. And so then we can look at each one of these and see which region they're in. So 0 is in this first region, so it's concave up. So this is a minimum. The second one, pi, is in the second region, is concave down, so that's a max. And the last one is a min. So the graph looks something like this. We start at a minimum at pi, we go up to a maximum with an inflection point in the middle at pi. Then we go down, we have a 0, and then we end at a negative inflection point at the bottom. I mean a minimum at the bottom of the graph. Okay, so that's the idea. So this would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. So why don't you all take a moment, pause the video, try this one, and then when you start the video up again, we'll try it together, and then we'll be done with this video for today. Okay, so if we do this together, we start by finding the second derivative, so that would be 2x minus 1. Then find the critical points by setting the first derivative equal to 0. We can factor this as x minus 3 times x plus 2. So we get x equals 3 and x equals negative 2. And then we can find inflection points by finding the setting the second derivative equal to 0. So add 1 to both sides, and you get 2x equals 1, divide by 2, and you get x equals 1/2. And so our concavity regions are 0, not 0, negative negative infinity to 1/2, and 1/2 to infinity. So we can plug a number in this first region into the second derivative, like 0. If we plug 0 in, we get 2 times 0 is 0, minus 1 is negative 1. So that's negative, so that's concave down. And then we can plug a number in this second region in, like 1. If we plug in 1, 2 times 1 is 2, minus 1 is 1. That's positive, so that's concave up. 3 is in this bottom region, so it's concave up, which means this is a maximum value. And negative 2 is in this first region, so that's a, oops, sorry, I did that backwards. So concave up means that this is a minimum. And the second one, -2, is a concave down, which means that this is a maximum. And so if we draw a graph of this, we'd start on the left-hand side. At -2, we'd get a maximum. At 1/2, we'd get an inflection point. At 3, we'd get a minimum. And then it would go back up. So this is x equals -2, x equals 1/2, x equals 3. Okay, and there's a sketch of what this graph kind of looks like. Without more detail, without the first derivative, we can't be any more specific than that. Okay, so that's it for this section. Make sure you're